Hello, and welcome to A Gross of Physics. Today is day 70, and we're going to look at potential energy. Now, potential energy, as we stated earlier, is stored energy, and it has different types. You could have stored energy gravitationally, and you could have stored energy in a spring or stretchy thing that we call elastic potential energy. We're going to start with gravitational today. Now, basically, when you lift an object up in the air, you're giving it energy. You give it potential to do work the higher you lift it. If you have more mass, it's going to do more work when you let it go and it hits the ground. So the potential energy is based on the mass and also how high you lift it. In fact, it's related to the force of gravity on the object and the distance it travels vertically. In fact, if we think about it, when you do work on an object and you lift it vertically, you're giving it potential energy. So the work you do will be equal to the potential energy that it gains. Now, when you apply a force vertically, you have to overcome gravity. So it's mass times acceleration of gravity, or mg. Finally, you lifted a distance up vertically. Now, we replace that d with an h for this equation, so we say it's the height that it gains. And when we do that, you end up with an equation for potential energy of mgh. Now, the m is the mass, g is the acceleration of gravity, 9.8, and h is the height you lift it. Now, what's odd about potential energy is that it's not an absolute scale. In fact, you would need the center of the Earth to be your 0 point all the time for that to work. Now, that really is not feasible for most problems. So what we're going to do is actually find the potential energy change, which is going to be much more useful. So it's going to be the change in potential energy that's going to be more useful for us than just the potential energy at a single point. Knowing the potential energy at a single point doesn't necessarily help us solve problems. So here's what we're going to do. We're going to take a specific point in a problem, typically the bottom, and call that our 0 point. And then the height will be based on that. So for many problems, it will be the ground or the table, or in some instances, the low point of a pendulum swing. So 0 is arbitrary in the problem, but what matters is how much it's changed. You can even have the 0 point in the midpoint of a problem, and then the potential energy below that midpoint would actually be a negative value. I think it's usually easier to stick to 0 as the bottom so that all your numbers are positive, because it's easy to mistake a negative and throw off the answer to the problem. So when we're talking about potential energy, we're really talking about the change in potential energy from a specific point. Now, going back to the pendulum discussion, a pendulum is just a mass connected to a string. We call the mass the bob. So we have a bob at the end of a string, and what we can do is pull that string back and let it go. And when we let it go, it's going to change the amount of energy that it has at different points. In fact, the potential energy is going to be a maximum at the end points of the swing and minimum at the bottom of the swing. So you're going to have your maximum potential energy at the two sides and your minimum potential energy at the bottom. Pendulums are going to be useful when we talk about conservation of energy soon, in the fact that as the potential energy goes down, the kinetic energy is going to go up, and you're going to have conservation of energy throughout the flight of the pendulum. Now, in any real pendulum, what happens is friction takes over and steals energy. So a pendulum's not going to maintain the maximum for long. In fact, it will constantly oscillate at a lower height each time. So if we're dealing with an ideal pendulum, we won't have any friction involved. And that will be useful for us to calculate conservation of energy later when we're dealing with pendulum problems, if we look at only like the first or maybe the second flight of the pendulum through the air. But over time, any real pendulum is going to slow down and eventually stop. Now, what we can look at for pendulums is the factors that affect the time period. A pendulum is something that oscillates cyclically. And what we'll find is that there are factors that affect the time period of the pendulum. That's something that we usually discuss in the laboratory setting. So I don't want to give away the answers here. But when the pendulum is moving, we often talk about its time period. Now, the time period is how often it completes one oscillation, or how long it takes to make one oscillation. And we count one oscillation as one back and forth motion of the pendulum. So as the pendulum moves through the air to the left and then to the right, or to the right and then to the left, we would consider one time period to be how long it takes to go back and forth. Some people would say to and fro. Now, consequently, we could find the reciprocal of that time period and find the frequency. So a pendulum is going to be useful anytime you're dealing with cyclic motion. In fact, because it's part of a circle, although the bottom part of the circle, it still experiences centripetal forces. So you can use a pendulum to talk about centripetal forces as well. So you might have to deal with problems where a free body diagram is involved. In that case, it's not just an energy situation. It's going to be energy or possibly forces involved as well. And in fact, when we get later on in the course, when we talk about waves, we'll be able to use pendulums to denote wave motion as well, because it's cyclic. So for now, pendulums will be useful when we're dealing with potential energy and ultimately kinetic energy when dealing with conservation. The total energy of the system is going to be constant. So if you have 10 joules of potential energy at the top, you'll have 10 joules of kinetic energy at the bottom, and then back to 10 joules of potential energy at the other side. And as it moves, you'll have a total of 10 no matter where it is, but it'll be partially kinetic and partially potential. The bottom line is the kinetic and potential energy of that particular pendulum would always add up to 10 in an ideal situation when we're not dealing with friction. That's getting a little ahead of ourselves and giving you some foreshadowing into our conservation of energy discussion. But for now, a pendulum can be used to deal with potential energy, mgh, if we know the bottom point and how high we lift it from that point. The mass of the pendulum, the gravitational pull, 9.8, and the height from the rest position will allow us to find the change in potential energy for the pendulum. That being said, we should look at a couple of practice problems dealing with potential energy. So we'll take the whiteboard out and do some practice problems now. Thank you. So the potential energy is a relative value. So mgh, the h really needs to be the change in height. We have to define a 0 point. And that's why pendulums, where we have a string connected to a bob, is lifted to a certain height. Now the height is going to tell me what the h is, but that's only if we decide that the bottom is our 0 point. So this will be our height, and we're going to go from 0 to whatever that height is. So when dealing with a pendulum, what we have is a situation where we should define the lowest point of the pendulum as our 0, and then the height will be however high we pull it. We can pull it to this angle, which would produce a smaller height. We could pull it all the way to 90 degrees, and that would mean the height is the same as the length of the string, but there's different ways that we can look at it. Even when dealing with a problem in class, what we may deal with is a situation where an object goes from point 1 here up to point 2 and then down to point 3. Well, what I often do is I'll call the bottom of the entire problem our 0. So at point 1, it's going to have some potential energy because it has a certain height. At point 2, it's also going to have potential energy. Not BE, PE. Because it has height. But at 3, potential energy is going to be 0. Now, if we called the potential energy 0 at point 1 here, what would happen is we'd have a situation where this would be potential energy is 0. This would be the potential energy that's positive. And then down here, we'd have a potential energy that's negative. Now, what I like to do is avoid negative values when possible. So what I'm going to do is always define 0 for my problems as whatever the bottom of the problem is. And that way I would have a 0 for this one, and then these would both be positive, like we had in the first example. But we could define even this point as the 0. It all depends upon your preference, and as you develop your problem-solving skills, you're going to define the height of 0 wherever you see it most beneficial to you. All right, for this one, we're going to hold a baseball 1.5 meters above the ground, and we're going to find the potential energy that the ball has. Now, baseballs are 145 grams. That's the standard mass. And that means if we're going to find potential energy, we would do mgh. I'm going to define the bottom of the problem as the ground. So potential energy equals, biggest pitfall is not converting to kilograms. So 0.145 kilograms times 9.8 meters per second squared times the height, which is 1.5 meters. We multiply across, and we will find the potential energy in joules. 0.145 times 9.8 times 1.5 yields 2.132 joules. Now, how fast would that ball hit the ground? What we would do with our tool set that we already have is we'd say VI is 0. We'd say A is negative 9.8. And we'd say D is negative 1.5 meters. And to find VF, we'd use equation 5. VF squared minus VI squared equals 2AD. So VF squared minus 0 equals 2 negative 9.8 meters per second squared times negative 1.5 meters. So you get VF squared equals 2 times 9.8 times 1.5, because the negatives cancel out, and you have 29.4. Take the square root, and you have 5.422, and it will be negative because we're talking about velocities. Now, the same thing could be said with the potential energy turning into kinetic energy. And that is going to be the work energy theorem that we'll discuss shortly. This will allow us to solve it using the potential energy that turns into kinetic energy. And effectively, if you look at this equation right here, we have 2AD. We don't have a 1/2 over here, so we might have brought it over. And the reason there's no mass anywhere is because potential energy has an mgh, so it's got a mass term. And you remember kinetic energy? 1/2 mv squared. So those masses are going to cancel. So it looks like equation 5 might very well be potential energy and kinetic energy combined without masses. We'll have to wait and see. All right, let's say we have a 1.2 meter long pendulum that happens to have 1/2 kilogram mass at the bottom, and we lift it up to the maximum height where it's 90 degrees there. Well, if we started here at 0 and we lift it all the way to the maximum that it can spin to 90, that means the height is going to be 1.2 meters. So to find potential energy at the top, mgh, 0.5 kilograms times 9.8 meters per second squared times 1.2 meters. So 0.5 times 9.8 times 1.2 yields a potential energy of 5.88 joules. Now, at the bottom of that path, what is that energy going to turn into? Well, we're going to be at 0 height. So the potential energy is going to become 0 at the bottom. This was at the top, the 5.88. Well, where did the energy go? Well, what happened was it turned into a new type of energy, and it turned into kinetic energy. So all of this potential has to go into kinetic. 1/2 mv squared. And what we can actually do is use that to find out the speed at the bottom of the swing. So if we just do that, 5.88 joules, because it all has to turn into it, equals 1/2 0.5 kilograms times v squared. So 5.88 divided by 0.5 divided by 0.5 again, square root, we're going to get v to be 4.85 meters per second. Now, what if it's not all the way at the bottom? Well, then some of the potential energy will go into kinetic, but it will remain, some of the potential energy will be kept. So we're going to look at more complex problems as we go. But for now, if we go from all to nothing, then all the potential energy is going to turn into kinetic. And if we were at the bottom, and now we go back to the top on the other side, over here, then all of that's going to turn back into potential energy. And what we're looking at is a situation where we'll go back and forth forever. The reality is friction will steal some energy, so it won't be as perfect as this. But theoretically, without friction or air resistance, this would go back and forth forever and constantly turn kinetic into potential and potential back to kinetic, back and forth over and over again. All right, now let's look at a student standing on a chair, and obviously that's either a very big chair or a very small student, and they are stepping off the chair and falling to the ground. Now the potential energy at the top, if they are mgh, 55 kilograms, times 9.8 meters per second squared, times 45 centimeters, which means I have to do 0.45 meters. All right, 55 times 9.8 times 0.45 gets me 242.55 joules. Now, like the pendulum problem, once this person steps off, all that potential energy is going to decrease, and it's got to go somewhere. It's going to go into making the person move faster, so kinetic energy goes up. When it hits the ground, or right as it's hitting the ground, potential energy will become zero, so that approaches zero, and the kinetic energy will be maxed. In fact, it will be a maximum value of 242.55, as long as we neglect air resistance. So we can actually figure out how fast that person's going to hit the ground. 242.55 joules equals 1/2, mass is still 55, v squared. 242.5 divided by 0.5 divided by 55, take the square root, and we get 2.97 meters per second. Now you could have done the same thing with VI is 0, A is negative 9.8, and D is negative 0.45 meters. And you'd use equation 5, which is VF squared minus VI squared equals 2AD. VI is gone. VF squared equals 2 negative 9.8 negative 0.45 meters. And I bet if we do 2 times 9.8 times 0.45 and take the square root, we get 2.97. The difference is this is a vector and it would be negative. This is speed and this is velocity. But it looks a lot like the same way to get the same answer. So there's a lot of similarities between energy and equation 5 that we did much earlier in the year.